Now I'm going to talk about magnetic torque. Now, what is torque? By definition, torque is a twisting force that occurs when we apply force to an object that is fixed on its axis. So if you consider a circular disc here and you put a bar that fixes the disc around the center of its axis, so when you apply force around it, it cannot move downwards. So what it's going to do is going to twist and turn the disc along its axis. So why is torque important? Because torque is the fundamental application applied in motors, electrical motors. By understanding the principle of torque, we can determine the speed, the strength, the output of our motor based on its construction and the properties. So we need to understand the properties that define a torque, and we can then apply them when we want to understand about the operations of motors. Okay, so to calculate torque, it's given as D cross F, where D is the moment arm. So as you can see from the figure, the D refers to the radius or the distance from the center point to the end of the cylinder or the disc, while F is the force applied to the disc, right? So these directions are governed by the following right-hand rule. So when the thumb of the right hand points along the direction of the torque, the four fingers indicate the direction that the torque tries to rotate the body. So if you put your thumb in the direction of T here, the other four fingers will point to the counterclockwise direction. That's why the force here is acting downwards. And if you find the force at the right hand side here, it's going to go upwards, the opposite direction, as it's going to go circular. Okay. So let's derive what is the magnetic torque if we have a rectangular coil shown in figure A here, and the rectangular coil is placed in a magnetic field B. So to simplify our analysis, we assume that the magnetic field or magnetic flux is moving in the positive X direction, and we have four sides segment: 1, here 2, 3, and 4. So note that for segment 2 and segment 4, it is parallel to the magnetic flux or magnetic field. So since we already know from magnetic force that when we have parallel between magnetic flux and movement of current, then that segment will not generate any magnetic force. So as stated here, there will be no forces on arms 2 and 4 because they are parallel to the magnetic field. So the force that is going to be generated in this complete circuit here will only come from segment 1 and segment 3. Now segment 1 and segment 3 is exactly identical, except the direction of current is opposite. So let's look at the equation. So for F1, which is segment 1, we refer back to the equation F1 equals to I dl cross B. So I is the magnitude of current. So dl, we have the differential length. The length of this segment here is B. And the direction is negative y because it's going downwards. So we have B in the direction of negative y. Okay. So for F3, we have exactly the same distance or the same length. So we have B, but the current is moving in the positive Y direction. So we have YB. Okay. And the direction of the magnetic field for both conditions or both segments is the same. We have a magnitude of B naught. We simply choose B naught because we don't know the actual value. So we take the magnitude and label it as B naught. And the direction is positive X. So when you cross product negative Y and X, you get positive Z. When you cross product Y and X, the direction of Y and direction of X, we will get negative Z. So the magnitude is going to be the same, I multiplied by B naught. So we get the magnitude here is the same. The only difference is now the direction is opposite each other. So if we look from this segment here, if we put our view from this segment here, okay, then we'll see this form here. So in other words, if we put it flat, now we see from top view. Let's see from front view, we'll see figure B. And we'll see that for segment 1, the direction of the force is going upwards in the positive Z direction. And force 3 is going downwards in the negative Z direction. Because the coil is fixed at its axis in the center, so it will rotate around its axis in this case, a clockwise direction. So the magnitude or the strength of the torque will depend on the distance from the center of the axis to the endpoint, here D1 and D3, or the radius, and the force itself. So the D1 here is going to be in the direction of negative X. And since we know that the length for segment 4 and segment 2 here is A, so the radius is half of it, A over 2. So this one, for D1, it's direction of negative X. For D3, it's direction of positive X. So we put it in the equation. Again, we apply cross product. So we get negative X direction cross with positive Z direction. We get Y, the direction of Y. Here we have positive X cross product with negative Z, so the sign is swapped. So you still get the same direction, which is in the direction of Y. So A over 2 plus A over 2, so you get A. So we have I, AB, B naught. So A is the length here and B is the length here. So basically when we have A multiplied by B, we are calculating the area of the rectangular coil here. So we can replace AB here with a capital A, where A is the area, and we have IA B naught in the direction of Y. Now, a simple way to increase the torque is by simply adding more coils. So the number of coils will directly affect the amount of torque that can be generated. So we know that T equals to D cross F. So it's also equals to, because this is a cross product, and we know D cross F is equals to dF sine theta, magnitude of D multiply with magnitude of F multiply with sine theta, the angle. So if we have a loop with n number of turns and we have a surface area A here, we can calculate the magnitude of the torque using this equation is equals to NIA B naught sine theta. So N is the number of turns, I is the magnitude of current, A is the area, B naught is the magnitude of the magnetic flux or magnetic field, and theta is the angle. Again here, we'll get maximum torque if theta is going to be 90 degrees. But since this coil is always going to move around its axis, so the value of theta is always going to change. Right. So NIA, N is the number of turns, I is the magnitude of current, A is the area. The multiplication of Ni and A is called the magnetic moment, and it sometimes is simplified into just small m. Okay, you should understand that this m here is N, I, and A. And we have the direction of n. Why do we have n? Why don't we have direction of x, y, or z, or theta, or phi, or r? It is because we use n because the direction always changes as the coil rotates around its axis. So for example, now it's tilted in this angle, so n is here. Once it's moved downwards, then the direction of n is going to change, and the change is going to be consistent. As long as there is a magnetic flux and there is a current flowing, the direction will always change accordingly. That's why we use n. So by definition, n is the surface normal of the loop and governed by the following right-hand rule. When the four fingers of the right hand advance in the direction of the current I, the direction of the thumb specifies the direction of n. So by replacing m and the direction n, we replace it with a vector capital, a bold M. So we can represent the torque in the form of a vector as torque equals to M cross B. So this is the vector form, this is the magnitude form or scalar form.